So for this part, I will be discussing about absorption factor or algebraic method for solving theoretical plates in plate tower, so for dilute gases and concentrated gases, and also determination of overall plate efficiency. So first, what is absorption factor? It is a measure of the solubility of a gas in a liquid. The equation is A is equal to Lm over mgm, where m is the slope of equilibrium curve, Lm is the liquid molar mass velocity, and gm is gas phase molar velocity. So, algebraic method for dilute gases. So, by assuming that the equilibrium and operating lines are straight and that the heat effects are negligible, Souders and Brown established an equation for computing for the composition of the exit gas as a function of the number of theoretical stages. And this equation is y1 minus y2 all over y1 minus y02 is equal to a raised to n plus 1 minus a all over a raised to n plus 1 minus 1. So n stands for the number of theoretical plates, y1 is the mole fraction solute in the entering gas, y2 is the mole fraction solute in the leaving gas, y02 is the mole fraction solute in equilibrium with the incoming solvent liquor, and this is 0 for a pure solvent. A is for absorption factor. And for the algebraic method for concentrated gases, here absorption factor varies throughout the tower, and this is due to the changes in temperature and composition. This is quite a problem, and so a solution was derived by Edmister using effective absorption factors A' and AE. So the equation derived is y1 minus y2 all over y1 is equal to 1 minus 1 over A' times lmx sub 2 over gmy sub 1 multiplied by AE n raised to n plus 1 minus AE all over AE n plus 1 minus 1. So subscripts 1 and 2 refer to the bottom and top of the tower, respectively. So the effective absorption factors used are defined by the equations AE is equal to square root of A1 times A2 plus 1 plus 0.25 minus 0.5, and A' is equal to A1 times A2 plus 1 all over A1 plus 1. Stripping equations. These equations are derived having the same assumptions that the equilibrium and operating lines are straight and that the heat effects are negligible. So for dilute gases, the equations are just analogous to the equations for gas absorption. Y is replaced by X, and S stripping factor is replaced to absorption factor A. And then for concentrated gases, so here stripping factor also varies throughout the tower, also due to the changes in temperature and composition. So it is also analogous to the equations for gas absorption equations. And it should be noted that throughout all the equations, the subscripts 1 and 2 refer to the bottom and to the top of the apparatus respectively, regardless of whether it is an absorber or a stripper. So this is done to maintain internal consistency among all the equations and to prevent confusion. These equations derived for computing for the theoretical number of trays assumes that the liquid on each tray is completely mixed and that the vapor leaving the tray is in equilibrium with the liquid. So in practice, complete equilibrium does not happen. This leads to the determination of overall plate efficiency. Overall plate efficiency. It is the ratio of theoretical number of trays needed to the number of actual trays used. So mass transfer theory indicates that for trays of a given design, the factors most likely to influence E in absorption and stripping towers are the physical properties of the fluids and the dimensionless ratio mgm over Lm, or the stripping factor. that's all for my report. The next report is about heat effects in gas absorption to be reported by Miss Alexis Jacobo.